Thank you so much, Lou, and thank you for inviting me. It's been an interesting visit so far, and I'm looking forward to the rest of the day as well. I'm going to talk about bridging algorithms, law, and practice. And so hopefully I can excite you about this research area on algorithmic fairness. And this is based on a stream of works with a lot of fantastic collaborators, where we spend brain cycles thinking about how to make algorithms with a positive impact to society, and a lot of fantastic students who've led different questions that you'll see in the talk. I'm going to mostly focus on hiring, but I hope to give you a sense of, what is bias and fairness to begin with, and some questions that we've been considering. So let's first maybe start with what is bias and fairness. And a lot of people like over the years, I've had many conversations going from, oh, that's an ethics or a philosophy question, to that's not a CS or a math question. And this was an article in Nature in 2018 that basically said bias is when scientific or technological decisions are based on a narrow set of systemic rules, structural social concepts and norms. So the resulting technology can privilege some people and harm others. And I thought this definition was nice because it touched upon these different aspects that we care about: technological decisions, social concepts and norms, privileging and harming certain groups. And these issues have sort of propped up in many recent news and articles and research. Although they are not new, they're just maybe more enhanced because of social media and our grasp on various technical platforms, like Amazon was providing same-day delivery to Roxbury, which was not providing same-day delivery to predominantly African-American neighborhoods in many cities. Roxbury was one of those. And when people raised this issue, and Bloomberg wrote a big article on that, then the mayor of the city called Amazon, and Amazon was like, okay, we are going to provide same-day delivery to Roxbury. Similarly, the next one is, the way we interact with rating systems. As humans, we are biased. We have our own biases in our head, and they may translate to ratings in gig economy systems. So for instance, Uber drivers' ratings were known to be biased with people's other characteristics other than driving capabilities. And so what should a platform like Uber do? Should they be like, we are just third party and we don't care, or should they actually intervene? And where we come in as mathematicians or operations researchers, right? Like, how can we help such platforms make these decisions? Privacy concerns. So Facebook was letting advertisers exclude users by race. That goes into bordering legal issues. And especially when the advertisements are credit applications are based on providing access to credit, access to loans. Okay. Sorry about that.
Is that because of the internet problem?
I don't know. The screen is flickering on my side. Okay.
So your screen is not still on.
It's not?
No.
Okay. Okay. Can you see my screen now?
Yes.
Yeah. Okay. All right. And then different kinds of error rates on different groups for image recognition algorithms, predictive policing practices, where more arrest records led to over policing in certain areas, but that was basically reflecting historic trends and practices, and automated experiments on ad privacy settings. This was a very nice study by researchers at CMU, where they claimed that, if a user they had fake user profiles that pretended to be male or female. So they controlled with that. And they said that males were actually shown much more higher paying job ads than females. Now, if you think from a recommendation engine's perspective, the recommendation engine is not designed to discriminate against any group per se, right? So recommendation engine might, I don't know what's happening. I'm sorry. Are you able to see online? Okay. No. Okay. Can I share my slides on your laptop
Yeah.
if that's easier?
Probably so.
Okay. So I'm going to send you a Dropbox link and um, good. So where was I? So automated experiments on ad privacy settings, which basically reflected differences in gender. These experiments showed that males were paid much more high paying jobs than females. And the question then is, does anyone go to a platform like Facebook or Google and write algorithms specifically to discriminate against a bunch of people? No, they don't do that. So they're learning some trends in the behavior and they're optimizing for click-through rates. And so the key point is that things that are driven by optimization or driven by machine learning, error rates, performance guarantees, these might end up discriminating against people because groups of people, because they might pick up some trends that eventually reflect in discrimination in terms of decisions. So here's the kind of questions I think about when I'm thinking about algorithm design or optimization design of different methods. The first is, what does it mean to be fair? You know, that's probably the first order question. What do we mean by fairness? And what is bias? And maybe in a static environment or a dynamic environment. So for instance, if I was placing facilities, like the diagram that you see there, that is the red points are facilities, and I want people to connect to facilities like emergency rooms. What does it mean to be fair? If it is facilities like trash dump sites or prison holding cells, then what does it mean to be fair? So that's a static environment. And a dynamic environment could be something like an electricity distribution network, where people have different demands, and these demands change over time, and you still want to have some sort of a reliable access to electricity in that scenario. What does it mean to be fair in that? The second question, which a lot of this talk will be about, is what is the impact of bias on data? What is the impact of bias on decisions? So we are going to look at decisions that pertain hiring and school admissions, but we've also thought about this in the application domains of police restricting and gig economy. So when you're matching job ads, what is the impact of biases and ratings and reviews on the final matches that happen? And the next question is, can we use these mathematical tools to help policymakers? Can we use it for detecting gerrymandering, or can we use it to detect, understand if we have limited resources, where should we invest those resources so it has the maximum positive impact? The third question is a little bit pertaining to other domains where there are experts in the domain that can really help us understand errors in data. So for instance, doctors in healthcare settings, they can read a patient's chart and understand which vitals are errored, because they can automatically correct for demographic correlations, right? So can we actually understand the domain knowledge and translate that into mathematical constraints that helps us ultimately make better decisions for people? And the last question that we'll touch upon in this talk is, how can we operate with all of these automated decisions in an environment which is also litigious? So how do we adhere to discrimination laws or price gouging laws? Price gouging is when sellers can increase the prices of the items when there is a shortage. And so California actually had a lawsuit where Amazon was sued for increasing the price of hand sanitizers, even after the California governor declared emergency. But Amazon is a retail platform, right? And so they were trying, it's online retail. So they were basically learning demand and pricing items accordingly. And so, right, so how can we adapt our algorithms in this landscape that is very litigious, and how do we operate with that? So in this talk, I'm going to focus on impact, policy, and law, right? So let's see how that happens. So this is an example of hiring in practice, where in summer 2020, Microsoft, Wells Fargo, Adidas, Google, all these companies were sued for a few $1 million for discrimination in their hiring practices from 2015 to 2018, okay? All right. And then they announced, in summer 2020, they announced that they're going to increase representation in senior management positions. But soon after that, there was the news that they were actually sued by the Labor Department for discrimination in hiring from 2015 to 2018. But then it seemed like their response to increase representation in senior management was a response to this ongoing lawsuit. So they were like, let's fix this discrimination problem in hiring and try to promote more African-American managers. But having done that, this is also a race-based claim. And so Labor Department again put them under scrutiny because they ran into reverse discrimination problems. So on one hand, if an entity like Microsoft looks at their past hiring practices, they don't see enough diversity in the hires and they're sued by the Labor Department for discrimination. But if they make claims to promote certain people based on the racial demographic characteristics, then they're again placed under scrutiny by the Labor Department for reverse discrimination, right? And so the question is, what can we do about it? And this is an example where on the face, in an oversimplified way, there is this legal tension between two laws, disparate impact and disparate treatment. So impact is when you look at outcomes of your algorithm and you see there is disparity in that, right? And disparate treatment is you look at your inputs and you bucket them into various buckets and say, I'm going to treat them differently. So if you treat everybody the same, you run into impact issues. If you treat everybody differently, you run into treatment issues. And so what does the Title 7 say? It says you cannot use protected attributes that are in this box. You cannot use this to make decisions in domains that are regulated domains. So education, public accommodation, housing, credit, and employment, right? And this is a growing list. So you see things like genetic information that are maybe not protected right now, but could become protected in a few years, right? So it's an evolving list. And this raises this question that how should a company like Microsoft fix underrepresentation in their pipeline without resorting to things like quotas? So if they just put a quota that we are going to hire so many people. Oh. So if you have, if they have something like quotas, then again, they run into anti-discrimination laws. Everyone with me? Okay. Any ideas on how we can solve the Microsoft problem?
So let me think it's very naive thinking, but
yeah.
For example, university hiring, faculty decision.
Yes.
Again, like all the advertisement very strongly, and isn't this just a mistake on their legal department in drafting their advertisement, or it's more than that?
Okay. So one idea is that it's a mistake in the legal department in drafting an advertisement that does not say that you value diversity.
Yeah.
What if your organization says they value diversity, but then you never see diverse people getting promoted, and then the Labor Department is like, okay, your job ad was basically fake on face value, right? Your organization is actually not doing things that act like built-in headwinds for minority candidates.
Oh, yeah. So, sorry. Yeah, that's very clear. So, what I meant was Microsoft already expressed the intent to hire, but
right.
They more explicitly expressed that, like, this comes as a
so good. So you're getting at Microsoft expressed the intent to hire or promote, in this case, African-American managers. So then why not other managers, and why is talent not a consideration there? Somebody should be promoted if they're qualified for that role, and not simply because they match check mark, right? And so that's where, so from our collaborator Devin on the law aspect, what we understand is that law is very contextual, right? So it's not like, as mathematicians we would like rules. We want rules, and we want things to, we can make algorithms that follow those rules, right? But that's not how law works. So we will come to some of these issues. Okay, good. So let's first try to model this problem mathematically. So we know that in hiring settings, data is biased. Evaluations data is biased. There are a lot of studies in psychology, in social sciences, that talk about disparities in economics, that talk about disparities in hiring rates, in the compensation, in the retention, in the reviews, right, across different demographics. So here's a list of studies. Emily and Greg are more employable than Lakeisha and Jamal. John's get better STEM offers than Jennifer's. This was a study conducted by Yale where they sent postdoc offers. John's got $25,000 more on average. Gender bias in academic recruitment. For assistant professors, the trends reverse. Females are preferred more, perhaps, and all the ways hiring algorithms can introduce bias. The reviews generated in a company might itself be biased. So if you try to learn on that and do resume screening, you're propagating those trends. So they had to scrap an AI recruiting tool that Amazon was developing. So all of this is even more problematic because 97% of Fortune 500 companies use applicant tracking systems. So they will input your resume, they will input your credentials, and based on your preferences, they are going to filter, and the company's preferences are going to filter resumes, right? And so this is like a huge barrier to jobs. And especially after the pandemic, like people don't have traditional four-year college degrees. They might have online degrees. Our data on people with non-traditional degrees is very limited. So you can imagine machine learning algorithms making more errors and then basically magnifying the problem even more, right? All right, so what can we do about it? I've just given you a lot of problems in the hiring setting. So let's see. So the first idea was, is it possible to quantify bias, right? And as early as 1970s, there were this article is quite old, on stereotype threats that affect performance. So this stream of work was done by Claude Steele, who was looking into University of Michigan admissions, and he studied academic achievement and student performance over the years. And he realized that for a stereotyped group, if you told them this is a test to test how good you are at this subject, so it's a high stress environment, the stereotyped groups will underperform. The non-stereotyped groups will not affect performance, as opposed to saying, oh, this is just a practice, we are learning here, then the performance differences were not there, right? And so he talked about how, you know, you could see differences in performance based on demographics, which also there are studies on low income and socioeconomic status. So the idea recently in 2016, 17 was that maybe we know it's an under or overestimation, and perhaps we can say something like a group model of bias. Okay. Perhaps we can say something that looks like this. So this was John Kleinberg and Manish Raghavan in 2018, where they said that let's assume, so this is our mathematical model, let's assume that people belong to these different groups, G1 to GK, people belong to these different groups, and within each group, there is some bias. So their potential is discounted by the same bias factor for all people who belong to a particular group. This was a very nice model. It's a very simple, it's not a very general model, maybe, but it does get to some of the core mathematical properties that you would like in algorithms. And this is something that we also observed in a data set from Department of Education. We plotted SAT scores across schools with low economic need index and schools with high economic need index. And we realized that there is a shift in the distributions. It's a consistent shift of about 0.8. That's the shifting factor. So that's the bias factor. That's the beta J, or 1.25, right, in the reciprocal. So we realize there's a consistent shift. And so using this model, then we can try to answer questions about how should we intervene, what kind of algorithms we can have to understand admissions better, to impact admissions better, right? But what's an issue with this model? Can anyone tell me what's an issue with this model? What's the problem?
The scalar, from a mathematical perspective, it seems that you're looking at a scalar object quantity and then analyzing that. I don't know whether multi-dimensional aspect is
Right. So perhaps multidimensional, or perhaps it's too simplistic. Like if my groups are left-handed and right-handed people, I've treated all left-handed people with the same factor, right? And so this is what we sort of proposed in 2020 with my student, that instead of assuming that we have ranking over all candidates, let's just have a partial order over candidates. So let me explain that a little bit more. Let's say we have these two candidates. One has a work experience of 0 years, a 3.5 GPA and a part-time, no part-time job. And this other candidate has two part-time jobs and a GPA of 3.35. If you were running a company, which candidate would you prefer? Would you prefer the one with the part-time job and a lower GPA, or the one with no part-time job and a higher GPA? How many prefer the first candidate, the one with the higher GPA? How many prefer the second one? Okay, so it's quite unanimous.
It also depends on what kind of job that person.
Yes, very relevant question. It depends on the context. Like, was this part-time job a fake part-time job? Was it a real one? Is it relevant to the job that we are considering, right? And so my point was that in this case, because over different dimensions, I have different values, it's harder to translate. And if I had maybe something like this, where work experience is 2 years and this is 2 jobs, it's like now comparable. And so maybe we can prefer the first candidate, right? In that case, maybe it's a clearer comparison. So fundamentally, we are getting to this idea that maybe looking at the data, we are not certain which candidate is better than which other candidate, right? And maybe we need to develop algorithms where we don't have a ranking of candidates, where it's not like you have a list of candidates from 1 to 100, right? You have some sort of a partial order. Okay, so let's develop this a little bit more. So here is, let's say, a set of candidates, and they have some work experience in GPA. And if I had to select, so this is just point-wise data, right? This is data that I'm taking at face value. If that was my data and I had to select 2 people, I could have said, okay, maybe select these 2. They're like the Pareto optimal of these candidates. Everyone with me? But now, because of disparities in testing, disparities are social biases. Maybe when we are reading a recommendation letter, we don't have an accurate estimate of the candidate. We have a biased estimate. This is something I saw in graduate admissions. Often letters on female students would have things also about, the last paragraph would be about baking skills or lab environment or planning activities, which would make them look less technical. And so we would consciously redact those things. We would consciously say that, okay, don't consider any of these other things and only review the first part of the letter, which does not have anything about baking and so on, right? So we have some of these. And so let's say we've somehow estimated that this is sort of the variability in the candidate's potential. From the data that we have, we cannot assess the candidate's potential accurately, and we have some variability in that. And so using this, now I can draw a partial order. So the pink candidate is definitely worse off than the green candidates. This green candidate is definitely worse off than these 2. But between these 3 candidates, we don't have a comparison because the work X overlaps and the college GPA could have been more. So I cannot reliably, given the data I have, I cannot reliably rank this candidate compared to these 2, right? So what does that give me? Now it gives me a tool to transparently account for variability in my evaluations data. If I can transparently account for that, maybe I can make decisions that are more diverse. So if I had to select 2 people, now I can say randomize over these elements, which are the maximal elements. Now, if I randomize over them, I still get some more people of this demographic. People that I initially would always rank lower than these 2 if I had point-wise data. Does that make sense? So I'm not saying that I want to be diverse and hence let's select like 1 green candidate and 2 candidates in the blue group, right? I'm saying let's be transparent about errors in the system. And given the best information I have about the errors in the system, let's be fair to everyone. Let's give equally qualified, robustly equally qualified people the same chance. So the goal has shifted from diversity to transparency. But transparency then induces diversity, maybe. That's the hope, right? Now, and so this is interesting because you might capture people who show the promise, who have the promise to be well qualified, even top people in the field, but you would have missed them if you only looked at nominal data. But now you're able to capture those candidates because you're looking for variability in the process. Yes? Good. So good. So I've basically not told you how to construct this, right? How do I construct these variability sets? And we're going to get to that question. Like, that's the key question. If I can answer how to construct that variability set for my organization, at that point, I can basically say, based on this uncertainty, this is the partial order, this is how I'm going to make my selection decisions, right? Yes. Yes, please. Please ask questions, interrupt me anytime. Yes.
It strikes me that what you're doing is very similar to social choice theory. You're of course familiar with errors with possibility theory. Your proposal to randomize
Right.
violates one of the conditions in errors and possibility theory. And I can't remember which one right now, but is that the concern? Or are you kind of trying to propose a principle that's consistent with traditional axioms in social choice theory?
So I think I'm going to give you some properties that I want this method to satisfy. And these are the properties like, if somebody is definitely better qualified, I want their probability of selection to be higher than somebody who's definitely lesser qualified. So I want to have some of these consistency properties, and I want to have some properties that also depend on the process. So we are going to develop some online algorithms with this, right? But definitely, like if you think about a situation where the variability for everyone is massive, everybody over intersects, everybody is treated the same, and now you're just doing a lottery, right? So your method in some sense is as good as these variability sets that you can construct. And that will have to be something that's statistically sound, legally validatable for this entire thing to work. Yes. Good. All right. And I don't know if people have heard about robust optimization, but robust optimization, so there are obvious connections, right? Robust optimization asks for decisions that adhere to worst case noise. Here we are going to select people even with the best case noise. So we're going to give them the best benefit of the doubt and then do the selections. So in some sense, it's the opposite of robust optimization. And the question that you asked, like, how do we construct these uncertainty sets? Right? So let me give you an example. Sorry, let's forget about this. So let me give you this example. So we looked at Aspiring Minds employability outcomes data set from 2015. This is a data set with around 300 candidates, and they have 300, 600, 600-ish about, and they have these characteristics that are filled out in the data set, characteristics that say gender. So this data set only had 2 genders, male and female. It did not have non-binary. The 10th class percentage, it's a data set based in India. So 10th class is standard 10th. 12th is another standardized national exam that happens. College GPA, college tier, English, logical, quant, some computer programming tests, and so on. So they have these bunch of characteristics about the candidates and their starting salary. So which job did they land and their starting salary. So what we did was, we just looked at computer programming scores by gender. So we made 2 groups of candidates. And by gender, they seemed relatively similar distributions. So you can see the blue and the red distributions, they are overlapping, it's relatively similar. So if you look at female candidates or male candidates, you see similar performance with respect to computer programming. And then machine learned on this metric. And we said, now I'm going to predict what your computer programming score is going to be. So I can predict how good you're going to be in a programming job, in a tech job. Yeah. So when we trained the machine learning model, it picked up a slight skew in favor of male candidates. So when we trained the machine learning model on this data, the linear regression model had those coefficients that you see up on the slide. In particular, with everything else being the same, if you flip the gender, males would get 16.95 points higher in the predicted computer programming score. So there was some bias that was picked up by the machine learning model. And this machine learning model is very transparent. It's a linear regression model. So I could look at what the coefficients on all of these variables were, right? But in general, if you're using a deep net or you're using a random forest, you may not even know what the coefficient on these is. So here's what we did. We said, yes.
16 point out of 700 total, is that right?
Out of, yes. So out of something like, I think 800 or something. Okay. Yeah. But that was the distribution of all the points, right? So it's still pretty significant, especially if I'm just looking at this number and I'm selecting candidates, right? Okay, good. Any ideas on how to use this information? Let's say you were in a machine learning team somewhere at Google, Facebook, the top tech companies, and you see this, that, you know, in the base distribution, you don't see any skew, but it's picking up a skew in the predicted distribution. What would you do? Regularize.
So you want the data, the generated data, or like the prediction of your algorithm to match with the ground truth data.
Right.
In reinforcement learning, we typically regularize with the ground truth distribution.
Okay. And okay, good. So I think we're doing something similar, but I was hoping like one of you would say something about just dropping gender, right? Drop gender and retrain your model. And so in algorithmic fairness, earlier the narrative was people were saying that, okay, maybe we should have fairness through blindness, that you drop protected attributes that you think are causing the problem and you retrain and take the best model. So it's the same decisions on everyone. But the problem is then if your underlying data is biased, you cannot correct for that bias, right? So just dropping those attributes does not work.
So Swati, you said that the entire data set is balanced.
Yes.
But the training data set is biased.
Training data set was, so this is the entire data set was balanced. Mm-hmm. And this is the skew in the training data set. So in the training data set, we see what the predicted score is and what the original, what the predicted score is.
So the training data set must be a subset of the entire
yes.
data set.
Yes.
Is there any particular
the training, no, the training data set was also uniformly sampled. That also did not show a skew.
So,
yes.
So the testing data set actually compensates the bias in the training data set, right? Eventually, when they add together, it's balanced. So if the training data set is unbalanced, biased,
right?
If the training data set is biased, the test data set must be the bias in the other way. Otherwise, when they add together, it cannot be balanced, right?
Right. So
suppose that I also have this main question. If your
yes.
data is training, the ground truth data is unbiased.
Yes.
And even if you are uniform, you select your training data by uniformly sampling that.
Right.
That data in this attribution is one dimension. That's not.
So okay. So one thing we need to keep in mind is that we are training the same model for both the groups. I'm plotting the two groups here, but I'm training the same model for both of the groups. I'm using the same linear predictor for both of the groups, right? And so if the female concentration in this data set is much smaller than the male concentration, and so for the small number of female, like, so if I had two linear predictors, then their slopes could be different. If I have one, my errors are skewed more, could be skewed more in one group, especially the minority group compared to the majority group, right? And that's like an artifact we are seeing here. All right. Yeah, good. So what we did was we did something like was suggested. we try to center the error distributions. So we said we are going to look at our training data, and we're going to look at what is the mean score and the standard deviation in that, the mean and standard deviation. And then we're going to look at the predicted training, predictions on the training data, and we are going to center that error distribution. So we're going to get what the standard deviation of the errors is. And that is something that we are using here group-wise to look at the intervals, that your error could be anywhere between minus some standard deviation and plus some standard deviation based on the group differences. And so that basically allowed us to construct these variability scores. This is not the only method. You can do something else. And in fact, we should do something much better than this. We should maybe get some counterfactual information, some multidimensional information. This is just predicting on one attribute, but at least it gives you a very concrete example of how this might look like, right? And so then we, for every point score, we had an interval. These intervals changed if you were male or female. And now the question is, in an application, instead of one-dimensional scores, you have a range. Then how do you adapt your algorithms to work on that? So that's the next question. Okay, so we've now given you one way of constructing these variability sets. Can we still make algorithms that are competitive or that have good performance with this data instead of this data? Everyone think? Make sense? Okay. I've either lost everyone or no questions? Okay, then I should ask questions. Next slide, I'm going to ask questions. Okay. How many people have heard of the online secretary problem? Okay, 1, 2, 3. All right. So online secretary problem is a classical problem in computer science that's been studied since 1960s to understand the trade-offs with partial information in decision making and performance guarantees. So here is an example. Let's say I want to select candidates for an Olympiad application. I want to select 2 candidates, and I know there are going to be 5 candidates who show up. And the game is that as a candidate comes, I have to make a selection decision. If I select them, they stay on the team. I cannot remove them. If I reject them, they will go and join some other team. So I've lost them forever. So every time a candidate comes, I need to make a select or a reject decision. And ultimately, I'll be judged for the value quality of the team that I have constructed, right? So let's do an example. So I know there are 5 people who are going to show up. I don't know what their scores are going to be like. I have no distribution information. When the first one comes, I will look at the score. It's Pilar with 90 points. How many people want to select Pilar already? Okay, 3 people want to select Pilar out of maybe like 20 in the room. So let's leave Pilar for now. And the next candidate is Sam, 70 points. How many want to select Sam? Nobody. Okay, so now it's already remorse building up. We should have selected Pilar and just gone with her, right? A lot of these algorithms actually work with a sample. So this yellow box that you're seeing on the slide is a sample. So I sampled 2 candidates out of 5. I got some sense of what the distribution is. And now let's look at the next one, 75, April. How many want to go with April? Nobody. But, you know, we only have 2 more candidates. So maybe April is still a good choice. We've not selected anyone so far, right? So let's select. I decided to select April. And now how many want to select Maya? Everyone. Of course, Maya is the best so far. Great. So we select Maya. And then the last candidate was Jad, who actually worked on this. And so he's fantastic. And but too bad, we've already filled out our team, right? And so this problem has been studied over many years. There's a long stream of literature, which is here. From 1963s, like Dinkin gave the first algorithm, which was constant competitive for the online secretary problem, where the goal is to maximize the total utility of hired candidates. So every time somebody comes in, you look at what the utility is, and finally you see what's the utility of the candidates you've hired. And you compare that to the optimum. Optimum is somebody who knows the utility of everyone and can select optimally. So you compare to that, and you compare, and that's the competitive ratio, the expectation of the algorithm. So you do randomized sequence of candidates, and you see how well you've done to the opt.
So from the job applicant's point of view, does that say it's always a bad idea to be the first one to be interviewed?
So excellent question, like positional effects, right? If you're the first one to interview, then would you always be in the sample and you're always rejected? And so there are incentive compatible strategies. So what people do is then select the first one with some fixed probability, irrespective of what the score is, right? So they would randomize. I either select a candidate just with a fixed probability, or I run the sampling algorithm.
Okay.
Yeah. So that reduces this incentive to appear late. We are not going to do that. And the question, so all of this literature has been there, but people have not really considered what if all this data was biased. That's like such a fundamental thing. All of these papers assume that you have access to the true utility of the candidates and not some biased values like, what if some students had some partial test, right? And so this led us to propose a biased secretary problem, where individuals arrive over time and post-set relations. So post-set is partial orders. As they appear, their relation to other candidates we've seen are revealed. And we want to be competitive where elements in the partial order can take any value W, any true utilities that are consistent with the ordering that we know. So if in the partial order, one candidate is definitely worse than the other, then for the first candidate, we can give like any utility like 90 or 80, and the other candidate could be 91 or 100 or 200. So it just has, numbers have to be consistent with the partial order. And then we try to bound this ratio, which is the competitive ratio, which is performance with respect to the optimum. So let's see what the model is again. So let's say first Pilar arrives. I have no data on anybody else. That's the only candidate. Then the next candidate, Sam, arrives. I cannot compare them, so that's okay. Then April is probably better than Sam. And so as candidates arrive, I get these partial relations between candidates that are comparable. And eventually I want to be able to select these candidates with better probability. Candidates that are the top, the maximal, the most performing candidates, I want to be able to select them with better probability. How much time do I have?
About 10 minutes.
Oh no. Okay. So we are going very slow. So I'm going to speed up. Okay. And basically what I want is in this model, these are the consistency properties, but I'll have to check what axioms and arrows properties like are violated. So that I'm not sure. So rank demographic parity basically says that if somebody is ranked higher, they should have at least as high probability of being selected as somebody who's ranked lower. And then it should also, they should be agnostic to the ordering in which candidates arrive. That's it. And so as long as the algorithm makes decisions on the just the post-set information that's available, it will satisfy this property that it's agnostic to isomorphisms. And then the probability, the monotonicity property is something that we enforce in the algorithm. So I'll tell you what the algorithm is to get that. All right. So the first idea is sort of any competitive algorithm must hedge across the top elements, right? So I should select each of these top elements with somewhat of an equal probability, because let's say I don't select from one of the groups. Let's say these are 3 groups of people. If I don't select from one of the groups, then I can drive that competitive ratio to 0. 0 or infinity based on how you define it. I can drive that competitive ratio to infinity, because the optimum can place basically on this one, I can place very high values, and on the rest, I can place very low values. So I need to hedge equally across candidates that are maximal in the post set. The problem with that is, let me skip this. Okay, so this was the algorithm by Dinkin. I think it's good for illustrative purposes in 30 seconds, that in the sample, you look at what the best element is, and as other elements arrive, pick the element that outperforms the best in the sample, the first one that outperforms the best in the sample. This algorithm is already E-competitive, which is optimal. And this can be extended very easily to selecting multiple elements. So that's your sample of 3 elements, and you look at the top 2. So here it's 7 and 9. And the algorithm is that you select the one that outperforms the second highest if it is in the sample. So let's see. So any number that comes up that's above 7, I'm going to pick that. So above 7 is 7.5, I pick that. Now the top 2 candidates are 7.5 and 9. So anything that is greater than 7.5, I'm not going to pick it because second highest is not in the sample. So now the second highest is 7.5. I get 10, but I don't pick it because it's not in the sample, because 7.5 is not in the sample. Now I update the top 2, which is 10 and 9. Now this is in the sample. So now I'm going to pick anything that outperforms 9. And so 11 is picked by the algorithm. So all I want to say here is, if you didn't get it, it's too fast. All I wanted to say here is that these algorithms are sample-based. You look at a set of elements, and then you pick things that are competitive with the sample. Or even if your sample size grows as you see more elements, you can adaptively update your threshold, and you can pick elements. And one can show that these algorithms are actually competitive. So you can bound the ratio in performance. Now, the question for us is the partial orders. And let's say we have these 2 partial orders, the poset with width 1 and width 2 and width 5. So here, if I pick any 2 elements, it could be that for some 2 elements, I don't know how to compare them. But if I pick 3 elements, then I can at least compare 2 of them. So width is the maximum set of elements that I can pick, which are all mutually incomparable. So that poset has more information because I'm able to rank more candidates compared to each other. This poset is very flat. It does not have enough information. The width is 5, right? If I pick the 5 candidates here, I have no information on how to compare them. And so somehow my competitive ratio should be bad for this poset. It should be better for that poset. So that already gives us a lower bound that we cannot do better than order width. Omega width is the lower bound, right? Now the question is, I don't even know what the partial order looks like before I've seen the candidates. So how do I estimate this width factor? How do I get that? And let me give you the algorithm here. So to get the width, what we do is we assign candidates to different labels. So as candidate come in, we give them a random group, and so it's like assigning a candidate to a random interview committee. We assign the candidate to a random interview committee, and we observe the partial order that is induced across different interview committees. Now, as we have a sample, now we have 4 labels, and we have a sample between those. This is enough to estimate the width. Once we estimate the width of the poset with the initial sample, we see if the size of the sample is enough, or do we need more? If we don't need to, is the sample size enough? So is this enough after estimating the width of the poset? If it is enough, then we don't sample more and we select the next element. Otherwise, we add more things to the sample. Okay. So this algorithm is quite nice because we can bound the competitive ratio. So we can bound it with respect to the width of the poset and some factors. Removing these factors is an open question. We believe it should be doable, but we don't know how. And the algorithm that we have has very nice practical properties, like to have independent interview committees and ask each of them to select the best candidate with the information they have. So it's very practical. And some competitive ratios, open questions, which have to do, for instance, what if the number of candidates is not known? I've assumed in all this that I knew how many candidates were coming. So if the number is not known, then your competitive ratios actually become much worse. Okay. So in this experimental study then, if we just used raw scores, it selected many more male candidates compared to females. The selection rate was twice as high for male candidates. If we introduced quotas would overcorrect. They would select much more female candidates than the data should have allowed, right? But when we developed these interval partial orders, with the interval like the error distributions, right? Then we saw that this now actually reflects the properties of the data much more. So you are actually able to be very sensitive to what you see in the data without overcorrecting just because you want diversity. And so the key idea was that enforcing quotas overcorrects, and accounting for inconsistencies can actually lead to nice, fair properties in the data. And this is in Wine and Management Science. So after this, maybe a key question to take away from this is like, how can we quantify variability in data? And can it help correct biases and downstream decisions, right? And with that, let me spend a few minutes on the anti-discrimination laws. So then we started thinking about how can this approach actually be made practical? Can it actually be something that solves the hiring problems that all these companies are facing? And so here's, because lawsuits are very contextual. So let's say there is a CEO of a company who says, I'm concerned that my workforce underrepresents, we don't get good enough candidates. I heard Microsoft got sued. Can we just do a 4/5 rule? Can we just do some sort of a quota mechanism across people that we are hiring? And just go ahead with that. And so what we started doing with our collaborator Devin and Jad is that we started looking at past lawsuits and looking at what are actually things people do in practice that are not useful. So what a lot of these third-party resume screening vendors do is that they will apply a 4/5 rule, which is if I'm recommending 5 people from a particular group, I'll make sure that at least 4 are recommended from some other groups as well. So they have this 4/5 rule, but that does not avoid discrimination. It just avoids a trigger for discrimination. And then we looked at things like this case, Ricci v. Di Stefano says documenting imbalances can allow a corporation to make changes. A plan must not insulate an individual from comparison. So if you're just promoting somebody because they're African-American, that is likely not to fly. People as numbers is not allowed. That's something that's disliked by courts if you treat a person, an individual as numbers. Posets can give us a transparent way of handling variability. If the variability in machine learning model goes down, then the posets will again become nominal data, which is perfect, right? Variability goes down and then you can make decisions based on nominal data. And there were some lawsuits where actually things like confidence intervals were allowed. So this is why all of this argument is in our upcoming UC Davis Law Review article, which basically takes the technical ideas and builds up a legal analysis of why these should actually be implementable and work in practice. Okay. Now, in the last 5 minutes, let me basically give you some more ideas and brief ideas with short stories. So models for variability in data can help us test various what-if scenarios. For instance, in understanding admissions in New York City, we realized that because of not bias, but a consistent trend of underperformance between high economic need index schools and low economic need index schools was not there, then somebody who was matched to the 88th ranked school could have been matched to a 51st ranked school, Like the disparity or the impact on minorities is much more. Impact on students who go to high economic need index schools is much more. And then mathematically, we could analyze this two-sided matching market to understand students who have potentials in certain ranges must be given some extra training, and that will have the maximum. That's like the social optimum. Social welfare is maximized when you target some students in some performance ranges and give them scholarships or additional training. The second idea after this was that errors in observed or recorded data may be due to a structured problem domain, may be structured. And so in a attempt to understand sepsis prediction, we looked at EMR data, which is electronic medical records. And we realized that a lot of these labs or measurements could be errored because of consistent biases. Like there's a pulse oximetry, which measures the flow of the blood through a visual lens. But then if you're darker skinned, then errors in that measure of oxygen are much more than if you're lighter skinned, right? And so in the electronic medical record data, we then worked with our collaborator who's an ICU doctor, Andre, and we figured out a lot of constraints that patients' data with normal physiology or patients' data who's sick could satisfy, or even physically possible could satisfy. And we use this to correct first the medical data and then run machine learning. And this allowed us to improve the prediction of sepsis by around 50%. It was a huge improvement. This work is joined with our collaborators at Emory and Grady, and it's on a submission to PNAS. And then I think this might be the second last question. Can OR help guide policymakers? And so this is an example where we analyzed the maps in Georgia, the congressional districting